audio articles presented by Off-Gassing, a scuba podcast, narrated by Daniel Porter.
Diluent Dilemma by Marc Crane. I have been diving CCRs or closed-circuit rebreathers for nearly 20 years, and I am qualified to not only dive a variety of models, but teach them as well. As anyone that knows me can tell you, I have a thing for rebreathers, and I recently had the opportunity to start using a new unit that was configured differently from what I normally dive. In any industry, it's important to stay up to date on the latest technology, but in the scuba diving industry, it's much more rewarding when you're able to actually use that technology. I have seen and used a wide variety of wonderful, as well as weird and wacky, ideas and configurations over the course of my rebreather career. What is happening now, however, is a paradigm shift from the established norm, and it is these norms that have governed and regulated our community. One of the major reasons for the standards development in the CCR community stems from the early days when there was a very limited amount of production units available. The standards on equipment that were set at the time are now outdated and obsolete in many ways. However, it is these training standards that must be upheld and maintained by instructors to remain compliant with their training agency, and therefore have some protection in the unlikely case of liability or litigation. What is a diluent? A diluent is a substance used to dilute something. But to answer that in rebreather terms, we first need to understand what a rebreather does. Rebreathers recycle the carbon dioxide expelled by the body and supplement the remaining oxygen by using a source cylinder of 100% oxygen, or as close as possible. Oxygen is our life-sustaining gas, but as we all know, too much of it at deeper depths severely increases the risk of oxygen toxicity, which can be fatal. Therefore, if we want to increase our diving depth on a rebreather, we need to thin the oxygen content down, which is exactly what diluent does. It reduces the partial pressure of oxygen and increases breathing volume, which allows us to increase our depth from a minimum of 6 meters to basically any depth you want. Traditionally, the cylinders that we carried on CCR units were small, with a finite amount of gas from an open-circuit gas consumption perspective. The cylinders used on the CCRs were typically between 2 to 3 liters capacity. Oxygen metabolic rates were calculated on a general rule of 1 liter per minute of oxygen, regardless of depth. So 200 bar in a 3-liter cylinder is 600 liters of usable gas, which can be equated to 10 hours of diving at any depth. The diluent is only needed during the descent phase of the dive or when the diver vents gas from the loop. Then more gas will be required to equalize the loop volume and allow breathing. Diluent is also required in the case of any kind of oxygen-induced emergency, primarily too much oxygen getting in the loop. In this event, we obviously want to get the oxygen concentration down as quickly and as effectively as possible. In the more traditional approach to rebreather design, where the unit was carried on the back and loop volume could be substantial, it was decided early on that the maximum partial pressure of our diluent should be around 1 bar ppO2. This varies from agency and locality, but for the purposes of this, we'll say 1 bar. This decision was made in part by wanting the ability to quickly reduce the loop partial pressure below 1.6 bar. If a standard limiting PO2 from open circuit were to be used, 1.4 bar PO2 traditionally, then you would be using a lot of diluent gas volume to effectively do this, something that you might not have in your small diluent cylinder. Now, if we look at the state of rebreathers today, they are still a niche market, but are more common on dive boats and at dive sites worldwide than they were 15 years ago. Also, with more than a dozen different types of units on the market, the technology has improved and the designs are much more reliable. Also, with more divers understanding the benefits of rebreathers, CCRs are being used throughout the spectrum of diving, from shallow reef filming to extreme deep cave exploration and everything in between. This has caused CCR designers to take their original concepts back to the drawing board. Rebreathers are now available in a wide range of configurations that are optimal tools for the educated explorer. One of the CCR configurations that is getting a lot of community acceptance is the side mount style rebreathers. These units differ from the more traditional CCRs by being either on the side of the diver, like a side-slung mount stage cylinder, or on the diver's chest. These options are mostly incorporating only one integrated cylinder in the actual rebreather, and that is the oxygen cylinder, otherwise the rebreather concept wouldn't work. So where do we source the diluent from? Rebreather divers have been carrying redundant life support gas backups in the form of a tank and regulator, commonly referred to as a bailout, for years. Something that is also required by all training agencies is that rebreather divers carry a bailout, and the PO2 of this can go up to as high as 1.6 bar in open water environments where a direct ascent to the surface is possible. What designers, manufacturers, and divers have now started to do is come up with a single solution for these units. Mixing the diluent gas requirements together with bailout gas needs in an emergency is a compromise on configuration and is being referred to as the dilout solution. Dilout solutions allow a great deal of flexibility, versatility, and adaptability for the rebreather diver with a mission. Carrying the diluent and open circuit bailout gas requirements in the same cylinder remove the amount of specialized gear as well as some potential failure points carried by the diver. Running the diluent from the bailout tank will also inevitably mean that the diluent PO2 is higher than the traditionally accepted 1 bar. This results from wanting to have an effective PO2 for bailout if you are forced off the loop. Traditionally, the diluent oxygen percentage had no bearing on your decompression obligation, as the rebreather maintains a constant partial pressure of oxygen and therefore optimizing any required off-gassing obligation. This would not be the case if the rebreather failed, and you would then be following open-circuit gas schedules. In this case, running a PO2 of 1 bar could significantly increase your in-water time as well as the required gas volume to safely exit. You do need to be sure that you then have adequate diluent gas for recovering the rebreather in the unlikely event of a problem arising, as well as ample bailout gas for a potential rebreather failure. If this has been planned and addressed, and depending on the type of CCR you opt to dive, the higher diluent PO2 will also extend the use of your oxygen. This is really only an advantage with the ECCR style units that have oxygen injected via a computer-controlled solenoid valve. Diving a MCCR with a higher dilout PO2 could see slight spikes in PO2 due to the constant trickle flow of oxygen into the breathing loop synonymous with MCCRs. Diving the ECCR with richer dilout will then see less oxygen being used and therefore could have the possibility to carry smaller cylinders, depending on the dive objective and logistics. What happens if the loop PO2 goes high but the diluent is oxygen rich? Units that are designed and configured to utilize the dilout solution are smaller in overall size, but more importantly, the actual breathing loop volume is far smaller than on some traditional units. Therefore, adding gas to a smaller loop from a larger volume cylinder has the same end result as a low PO2 in the small diluent cylinder on larger loop volume traditional unit. Let's do a simple calculation to demonstrate. A 30-meter dive using a dilout of 32% means that the PO2 is 1.28 bar, which is approximately the desired PO2 set point we want for our dive. This means that for the deepest section of the dive plan, it is actually the diluent that can be used to maintain the desired level of oxygen in the loop. As we go shallower, the oxygen will again be introduced into the loop via the solenoid to maintain our desired constant PO2. This all sounds pretty straightforward and simple. However, it is still critical to carry enough gas reserve in case of needing to bail out. Unfortunately, this is something that a lot of rebreather divers neglect to take into consideration, or they rely too heavily on the team around them. But that is a different story. On a traditional CCR, the diluent is encased on the unit in a small cylinder, and the diver carries a separate bailout system for redundancy. The onboard gas would normally be air, and the selected set point in the range would be 1.2 to 1.3 bar PO2, depending on the dive plan. If we assume the set point has been put to 1.3 bar, even with an air diluent, the CCR will be supplying the diver with a nitrox 32.5% or 1.3 bar PO2 set point for ATA. And the diluent is there to reduce the oxygen concentration, so the diver would probably select a nitrox 32% fill for his bailout. The dilemma that the diver using a dilout solution has is that if air was selected and the diver is forced off the loop due to a problem, then the diver would be breathing a much less efficient gas mix at a time where you would be needing to expedite your exit from the water. This is one reason why, as a community, we are slowly accepting the concept of dill-out. However, this is not something that is being mirrored in the certification agencies. The state of standards and the liability game is the big driving force in all areas of diving. Unfortunately, this activity is not risk-free, and serious injury or death can be the result of a badly planned dive or misjudged situation. This is another reason why instructors carry third-party liability insurance, as it's the instructors that are at the sharp end in the event of an incident, and would need the coverage to pay for fees and potential damages. Training agencies create standards that are approved by insurance underwriters, and these standards need to be adhered to by the instructors teaching for that particular training agency. So here's the thing. The niche market of rebreather diving has been set up based on the standards developed from the entry of the early units into the market. So a lot of the limits, protocols, and procedures base themselves firmly in the more traditional CCR design. Currently, the standard set by RESA, or the Rebreather Education and Safety Association, is limiting the diluent PO2 to max 1.1 bar. And even though this is not the definitive global standard, it is something that most training agencies also base their standards on. The ISO standards for rebreathers is currently being finalized, but this will also be based largely on the RESA recommendations. This basically means that currently there are no amendments being considered for units that do not utilize a traditional oxygen diluent gas approach, but instead are designed and configured to run a dill-out solution. Therefore, if we opt to dive a dill-out solution, where does this leave us in case of an accident or incident? Will our insurance cover us, or is it a get-out-of-jail-free card for the policy suppliers? Standard gases are also something that make the diluent dilemma even trickier. Depending on where you are diving and the logistics available, getting a particular fill may be difficult. I switched to just running either nitrox 32% or Trimix a few years back, and very rarely have good old-fashioned air around. This traditionally is no big deal, as I prefer to run light Trimix mixtures on the CCR below 35 meters anyway, and adding a Trimix to a 2 or 3 liter cylinder is a no-brainer. However, the unit I recently started to dive uses a dill-out solution, and as I am still building up my experience with it, I am not venturing much deeper than 30 meters, and therefore opt to run a 32%. This increases oxygen efficiency in the small onboard cylinder and gives me lots of effective bailout in case of an emergency. It does, however, violate the limits of my certification, which in the event of an accident could cause issue with my insurance. The use of rebreather systems that are designed to be configured and utilize a dill-out solution will remain and most likely gain popularity. These systems provide a lot of additional gas redundancy and therefore time, both during the dive phase as well as in case of eventualities or emergencies. As deeper rebreather diving gains in popularity and bottom times are increased to allow more time documenting wrecks or marine life, so will the drawbacks and limits of carrying multiple cylinders for bailout shift towards utilizing dual or bailout rebreather systems. These bailout rebreather systems will more likely than not run a dill-out solution. Therefore, for the sake of both divers and instructors, do manufacturers need to approach training agencies and clarify the PO2 problem for diluent? Ultimately, the buck stops with us, the divers, as we need to constantly be aware of our level of knowledge and experience by understanding the dynamics of the rebreather that you opt to dive and selecting diluent based on your chosen unit and your specific objective. Participating in remedial training and signing up to participate in skills updates with an experienced instructor that performs the type of diving you wish to be involved with are all critical.
Offgassing, a scuba podcast.